7.1 Integration by parts. Every differentiation rule has a corresponding integration rule. For instance, the substitution rule for integration corresponds to the chain rule for differentiation. The rule that corresponds to the product rule for differentiation is called the rule for integration by parts. The product rule states that if f and g are differentiable functions, then d over dx, open bracket, f of x, gx, g of x, close bracket, equals f of x, g prime of x plus g of x, f prime of x. In the notation for indefinite integrals, this equation becomes the integral of open bracket f of x, g prime of x plus g of x, g prime of x, f prime of x, close bracket dx, equals f of x, g of x, or the integral of f of x, g prime of x dx plus the integral of g of x, f prime of x dx equals f of x gx. We can rearrange this equation as equation 1. The integral of f of x, g prime of x dx equals f of x, g of x minus the integral of g of x, f prime of x dx. Formula 1 is called the formula for integration by parts. It is perhaps easier to remember in the following notation. Let u equal f of x and v equal g of x. Then the differentials are du equals f prime of x dx and dv equals g prime of x dx. So by the substitution rule, the formula for integration by parts becomes equation 2. The integral of u dv equals uv minus the integral of v du. Example 1. Find the integral of x sine x dx. Solution using formula 1. Suppose we choose f of x equals x and g prime of x equals sine x. Then f prime of x equals 1 and g of x equals negative cosine x. For g, we can choose any antiderivative of g prime. And thus, using formula 1, we have the integral of x sine x dx and equals f of x, g of x, minus the integral of g of x, f prime of x dx equals x, open, negative cosine x, close, minus the integral of open, negative cosine x dx plus cosine x close dx equals negative x cosine x plus the integral of cosine x dx equals negative x cosine x plus sine x plus big C. It's wise to check the answer by differentiating it. If we do so, we get x sine x as expected. solution using Formula 2. Let u equal x dv, so u equal x, du equals d of x of dx. Restarting by going to the sidebar. It is helpful to use the pattern u equals whatever, du equals whatever, dv equals this, and v equals that. Back to the solution using Formula 2. Let u equal x, and then du would equal dx, and dv equals sine x dx, and v equals negative cosine x. And so the integral of x sine x dx equals the integral of x sine dx equals x open negative cosine x close minus the integral of open negative cosine x close. Excuse me. Redoing this line, the integral of x sine x dx equals the integral of x sine x dx equals x open negative cosine x close minus the integral of open negative cosine x close dx equals negative cosine equals negative x cosine x plus the integral of cosine x dx equals negative x cosine x plus sine x plus c. Note, our aim in using integration by parts is to obtain a simpler integral than the one we started with. Thus, in example 1, we started with the integral of x sine x dx and expressed it in terms of the simpler integral, the integral of cosine x dx. If we had instead chosen u equals sine of x and dv equals x dx, then du equals cosine x dx and v equals x squared over 2. So integration by parts gives the integral of x sine x dx equals open sine x close x squared over 2 minus 1/2 the integral of x squared cosine x dx. Although this is true, the integral of cosine, the integral of x squared cosine x dx is a more difficult integral than the one we started with. In general, when deciding on a choice for u and dv, we usually try to choose u equals f of x to be a function that becomes simpler when differentiated, or at least not more complicated, as long as dv equals g prime of x dx can be readily integrated to give v